Welcome back to KTAL LP FM in Las Cruces, New Mexico at 101.5 on the dial, also streamed live at lccommunityradio.org. We just finished a segment with two of the students from the Las Cruces Academy, which is a nonprofit private school that I'm also associated with. My name is Vince Gutschick. I guess I didn't mention that in the first segment. The students are Kira Durrett and Arabella Camuñez, and we'll get back to them in a later segment today. And I should mention that besides the streaming, we have recorded the earlier shows. Well, there's only one show, and I have put that up on my website, which is science-technology-society.com. And there I discuss all kinds of aspects of science and technology and social issues. You go to the homepage and you'll find that segment with a link to the recording, which is up on YouTube. Let me follow up on something that came up peripherally during the segment with the two students, and that touches on astronomy. Okay. Earlier, maybe 8 years ago, in fact, I wrote a little essay called "You Make More Heat Than the Sun." I'll just dive into that. So I lead off with, say what? The sun's temperature is surely much higher than your temperature, our temperature. In fact, in absolute units, the temperature of the sun is nearly 20 times hotter, nearly 5,800 Kelvin in scientific units. That's about 5,500 degrees Celsius, and I have to think, almost 10,000 degrees Fahrenheit. So we, in our bodies, run at around 310 Kelvin, about 37 degrees Celsius. So per unit of area, the sun obviously puts out an enormous amount of energy. In fact, it's to the fourth power of the temperature. So it puts out, 20 to the fourth times more power than our bodies does at the surface. Of course, it's a lot bigger than any one of us or all of us put together. It has a mass that's about 330,000 times the mass of our own Earth. And the Earth's mass is about 86 sextillion times more than our own body masses of around 70 kilograms. By the way, that's 10 to the 21st, 86 followed by 21 zeros. But the statement is true in an important sense. The average kilogram in our body generates more metabolic heat than the average kilogram of the sun does with its nuclear reactions. So let's figure out how that's possible. Well, at rest, one of us, and they always pick the 70-kilogram male, and I don't know why, it's not very fair. We're putting out about 70 watts just sitting there. That's about 1 watt per kilogram. And we have to eat to maintain that rate. You can go through all of the calculations, and it turns out that we burn up about 1,560 kilocalories, food calories, in the old units. It's about 6,500 joules in the scientific units. Of course, we have to do a lot more than that. If we're more than minimally active, it can go up to 10,000 calories if we're climbing mountains or skiing across Antarctica. And people have done that. A Japanese fellow skied across Antarctica. Well, I guess he went to the South Pole. I don't know if he skied back. He was drinking liters of olive oil. He had to train himself to do that in order to get enough calories. Okay, so keep on going. How do we figure out how much power the sun is putting out? That's energy per unit time. Well, almost all of the energy coming out of the sun is in the form of electromagnetic energy. Everything from radio waves, pretty weak, up through ultraviolet. If you gamma ray or X-rays, really. Very few, mostly near the visible range and the near infrared. Okay, by the time that power reaches the surface of the Earth, it's about 1,000 watts on a square meter. Okay, a square meter is a little bit bigger than a square yard, and 1,000 watts about a hairdryer's worth. So above our atmosphere, it's higher. Some stuff gets reflected and so on. And it's 1,360 watts per square meter. Now, of course, as you go closer to the sun, you're going to get much more intense radiation. Figure it this way. Put a sphere around the sun at its surface, which is not a solid surface, it's a big gas ball. And you can capture all the energy there. And then expand that sphere to the radius of the Earth's orbit, and that same energy is now spread out over something that's proportional to the square of that ratio of distances. So we are 215 times farther away from the center of the sun than its own surface is. That means that the radiation at the surface of the sun is 46,000 times higher per area than it is at the Earth's surface. And then you take the area of the sun, which you can calculate as 4 pi, remember pi, times the radius of the sun squared. That area, by the way, is 6.1 quintillion square meters. That's 6.1 followed by 6 followed by 18 zeros, forget the one. And if you put it in English units, 2.36 trillion square miles. You could put 1 million U.S. Areas of the U.S. across that surface of the sun. Anyway, you take that area and you multiply it by the power density at the surface, and what you find is that it's 382 septillion watts. That's 3.82 and then times 10 to the 26, which is 26 zeros following the decimal point. Now, we've got to figure out the mass of the sun, and I won't lead you through all the details, but it's 2 times 10 to the 30th kilograms. That's 2 followed by 30 zeros. It's a lot of mass. So if you take the total power from the sun and you divide by its mass, you get 0.00019 watts per kilogram, 190 millionths of a watt per kilogram. So we're running at about 5,000 times that intensity on a mass basis. So that seems to be a trend even if you look at animals on Earth. You take us and go up scale to something much bigger than us. Take an elephant. Its power output per unit of mass is lower. And if you go downscale, you go to a tree shrew, then it has much higher output than we have per unit mass. Good reason for that. As you gain more volume, as the sort of cube of your dimension, your surface area on which you can lose heat is only going up as the square. So an elephant that had our metabolic rate per unit of body mass would overheat drastically. Now, if the sun were to match our output of power per unit mass, it would be 5,000 times more intense than it is now. To do that, it would have to be over 8 times hotter, and that would bring its surface temperature up to about 50,000 degrees, or 50,000 Kelvin. There are some stars that approach that. The blue supergiants, Eta Carinae is a relatively nearby star, as I recall, and that reaches 40,000 Kelvin. But if you wanted to be near one of those stars, you'd better bring a lot of sunscreen, like SP 50,000, because it's almost all ultraviolet and far ultraviolet. It also wouldn't last very long. These big stars burn out, and they also pulse. They go expanding their radius and so on. You wouldn't live long enough. We wouldn't be there long enough to evolve into intelligent beings, assuming we are right now. Anyway, we'll take a break here. And remember, you're listening to KTAL LP FM in Las Cruces, New Mexico. We're at 101.5 on the dial. We're also streamed live at lccommunityradio.org. We'll be back in a few minutes. Thank you.